Jesse. I'm here today to talk about my Google Summer Code project about finite Naperian functors and Hasktorch. So I'd like to thank my mentors, Junji, Austin, Sam, and Dominic. And let's get started. So, quick overview of what I'm going to talk about. I'm going to give a 3-second overview of Hasktorch. The talk later today by Junji will go into a lot more detail than I will. I'm going to give a quick explanation of Naperian and finite Naperian functors, trying to give enough information for non-Haskell people as well. And then I'm going to talk about how to integrate the two. So firstly, Hasktorch is a library for tensors and neural networks, and it leverages the fast backend bits of PyTorch, which are written in C and C++. And today I'm just going to focus on the tensor aspect of it, so just the multidimensional array aspect of Hasktorch is where my work is relevant. So there's some tentative, unofficial design philosophies for Hasktorch. I don't think they're anywhere, but they're good to go by. So, because we're working in Haskell, there's a bias for pure functions. Thankfully, PyTorch and the backend are also quite pure, so it's a relatively good match. We don't want to be too opinionated. We want people to be able to build what they want. So a layered typing approach or allowing multiple front ends is a good thing to aim for. Functionality over representation. No one wants to use a slow machine learning library, especially if it's built on top of a fast one. So actual performance is very important. And if there's any required complexity, try and push it into library internals. So these are what we're going to grade against at the end to see if we were successful. So Naperian functors. So if anyone knows Haskell, they're restriction on Haskell functors. But for those who don't, essentially, a Naperian functor is a specific data type, which can hold whatever value you want, and it's equivalent to a function which maps the indices to values. So an example would just be like a vector length 5, and then this log f thing, the indices would be the numbers 0, 1, 2, 3, and 4. A non-example, for example, is lists, where you can index off the end of the list, so you couldn't write it as a function like this. So that's a simple non-example. For Haskell people, it's equivalent, naturally isomorphic to that type as functors. But for everyone else, what this means is we have two functions, lookup and tabulate, which provide an isomorphism between the function representation and the actual data type. And there's also interactions between mapping over that data type and these isomorphisms, which basically let you move things around. And this F map, this map is a normal sort of array-based map where everything works pointwise. And of course, we can also do binary operations pointwise as well. And this is the same applicative instance as it is for functions. But yeah, a good reference is applicative programming with Naperian functors. So let's give some examples. So as I mentioned, a fixed length vector is the simplest example, I guess, of Naperian functors. You can also have other fixed shape data structures, like a specific fixed shape tree or a graph. You can also combine Naperian functors together. So you can take two of them and take the product. And the reason why that's a Naperian functor is because you either give a left index or you give a right index, and that lets you index into it. You can also compose them together, so just like you can have an array of 2 dimensions as vectors and vectors, you can nest them together, and then you just need a pair of indices to go one level and then another level. So in pictures, if we have a tree, the type of trees of that specific shape right there, holding values of type A, well, that's equivalent to a function which, for each position of the tree, gives you a value, and so you can go back and forth. So there's an example, which isn't a vector. So what are finite Naperian functors then? Well, finite Naperian functor is just when that indexing data type is finite. And this gives us more structure, because essentially what we've done is we've said this data type really, it's essentially just a fixed size vector. But we don't want to think about it as a fixed size vector, because then you may as well just use fixed size vectors. Instead, we sort of want to give semantic meaning to the indices and how they relate to each other. For example, a tree. Okay, sure, we saw, it holds 5 things, so okay, it may as well be a vector. But we don't want to think about it as a vector, because say, for example, we're doing some reduction operations. Well, we want to reduce the leaves in pairs, for example. So there's more semantic information. And so even though it's isomorphic to a fixed size vector, we want to view it as something more. So as we saw, we can compose Naperian functors. You can also compose finite Naperian functors, so just like nested fixed length vectors. If it's a nested fixed size thing, you can do the same thing, and that's sort of a generalization for multidimensional arrays and tensors. And this isomorphism to a fixed size vector lets us do things which we're used to. So for example, we can do reduction operations, such as maximum and averages, and we can also linearly sequence effects, for example, random initialization or differentiation or something like that. And so by restricting ourselves to these finite ones, it gives us the ability to everything which we want numerically as well. So what should a generalization of a tensor using finite Naperian functors look like, and how can we use it? So just as multidimensional arrays are conceptually just nested vectors, I think there's more to it, especially with memory layout and whatnot, but we can do the same sort of thing. So if we just take the finite Naperian functors and nest them like you would nest vectors, then we're going to use this data type to describe the thing on the left. And so we have a type level list of the things that we're storing. So for example, this could be a vector of like 5, or it could be that tree which we gave. And so this is the pure Haskell generalization with finite Naperian functors for tensors. So how can we translate between them? There's a fundamental mismatch, which is this data type can hold any Haskell value, but of course, when we're working with actual memory, we're not going to store integers. We want to store, actual data like fixed length floats. So how can we work with this mismatch? What we can do is we can sort of just instantiate the Haskell data type with the underlying Hasktorch tensor. And so we sort of have a tensor which the top half is Haskell and the bottom half is Hasktorch. And we can always make sure that we never completely leave the Hasktorch side. And so visually what we can do, for example, we can say, okay, well, we have an underlying Hasktorch tensor, which is a 5x4 tensor. Let's say we want to treat one of the dimensions as a tree because we want to do a reduction fold over it or something like that. What we can do is we can use a function which automatically takes the original matrix, produces views of the matrix, so no memory copying, and places each of the views in the proper place in the tree. So I've labeled it with the indices. And then this is just one function, and that would be exposed to the user. And here we get the advantage of using the vector isomorphism without having the user trying to do anything. And we now get to add more semantic meaning to that axis of the array. And additionally, we can use this representation to sort of take all the Haskell functions that you might be used to, like map or duplicative instance functors, or duplicative instance functions, or traversal, whatever, and basically just specialize them so that they're still parametric over the dimension and the underlying data type of the Hasktorch tensor, but it still provides the sort of same API that everyone's used to in the type classes. But in the end, since we never end up leaving Hasktorch, it's still going to be as performant as you could ask for, because none of the data ever leaves Hasktorch. So it's the best of both worlds. We only use torch data structures, which, as a bonus, means that the gradient bit of torch should sort of just work because we never marshal any data, everything stays there. There's some polymorphism still, so we get some of the advantage from using normal Haskell type classes, even though we actually aren't. And you can write something that looks like idiomatic Haskell while still having full control of how the data is arranged. So let's grade against the design philosophy. Well, we didn't introduce any impure functions. Okay, good. We created just purely an outer layer, so we didn't force any opinions on anyone else. The user has full control over the data layout, and also automatically uses memory views instead of copying stuff around. And finally, we track the sizes and automatically use views and automatically put data in the right indices and allow you to go back and forth. And yeah, that's everything for now. And basically, the next step is to try and write a compelling example which doesn't break somehow. Yeah.
very much. I realise we're running into coffee time, so only maybe just one or two maximum questions, then you can talk to them.
So you chose PyTorch as a backend, that's great, but you have probably had a choice to make. Why that versus say TensorFlow?
So I mean, my project was specifically do something for Hasktorch. So
Nice.
yeah.
No choice.
I don't think there is a.
But I mean, because TensorFlow is
Tensor
number one
is-
currently, and PyTorch is number two. So
Okay.
it's still reasonable choice.
One more quick question, otherwise it's coffee time. Great, well I think that's a fantastic session. Thanks very much everybody.